welcome to Conversations on Ichnology. The International Ichnological Association is pleased to offer this lecture cycle to all those interested in ichnology. The lectures take place every last Friday of each month until November, and we always try to seek a compatible time with most regions of the world so that more and more people can participate. Thank you for joining us for this fourth lecture. Also, thanks to our IIA members for their support of our association. The IIA is committed to assisting as many students as possible in participating in IGNIA 2028, and more members are needed to accomplish this goal. Beginning this year, our association provided new member categories that make memberships more accessible to all. Thus, we invite those who are not yet members to join the IIA. Well, about today's talk, Ricardo Melchor obtained his degree in geology from the National University of La Pampa and his PhD in geology from the National University of La Plata in 1995. Ricardo mostly works on sedimentology and ichnology of continental successions, including vertebrate and invertebrate ichnology, as well as neoichnology. He is a principal researcher from the Argentinian National Research Council, CONICET, and professor of sedimentology at the University of La Pampa. He is the author of more than 80 papers in international and national journals and book chapters, and has taught several postgraduate courses on sedimentology and continental ichnology. His research mostly focuses on the ichnology and sedimentology of desert environments, both fossils and modern ones. And in this opportunity, Ricardo will share with us the talk titled The Study of Fossil Vertebrate Burrows. Thank you very much, Ricardo, for accepting this invitation.
Hey, thank you for the invitation to give this talk. I will try to talk about some aspects of the study of a particular kind of trace fossil, which is vertebrates, fossil vertebrates, burrows. And this is more or less a new area of research. To my knowledge, the first account of a fossil burrow was in 1933, and there are an increasing number of publications in the last years. And the focus of my talk is to highlight some aspects of the study of vertebrate burrows. And the image that you are seeing today, I hope, it's a composite of some aspects that I will try to explain or develop in my talk. And the study of fossil vertebrate burrows, the application of different techniques, and with a relationship with a neoichnological observation of modern burrows, which is very important to my knowledge. I started to work in fossil vertebrate and modern vertebrate burrows about 15 years ago, first with Jorge Genice, but a good deal of what is presented today is related with the doctoral PhD thesis of Cristina Cardonato, my wife, you might know. And she is retired. She didn't want to participate of this talk, but I'm sure that many of the aspects are derived from her work. Sorry. The talk online, I will try to distinguish major groups of vertebrate burrows. Some architectural element of the burrow systems, some important measurement that we can obtain from the field, an emphasis on the cross-section shape of the tunnel or ramp of the burrow, the details of surface ornamentation, the burrow fill, the sediments filling the burrow, and the main inference that we can make from this element of these features of a burrow. Hope you can understand me, and I forgot to say, to say that I hope that you can understand due to my poor English, and I try to put a lot of text in the slide so you can understand, I hope. One of the measured group of burrows, vertebrate burrows, are those of amniotes. These are, in general, forming ramps of low-angle burrows or sub-horizontal system. This is the case of armadillos, varanus, or rodent burrows, which I picture here. All the diagram are in cross-section. And amniotic burrows are mostly at high angle to the sediment. This is, for example, toads, frogs, or lungfish burrows. One of the main reasons for this difference is an energetic reason. There are some studies that have reached the conclusion that when a vertebrate is burrowing in the substrate and the inclination on the slope is greater than 40 degrees in subaerial settings, a significant increase in energy is needed to complete the burrow. And here we can see an unrealistic situation when an armadillo is trying to burrow a subvertical burrow and the earth comes inside the burrow. But for this reason, armadillos usually dig sloping burrow, low ramps or sloping burrows are decreased between 30 and 45 degrees. So they can scratch on the front, come back, push back the air, and from time to time emerge to see what is going on, and then continue your work, but always at a low sloping ramp or burrow. Amniotic burrows are in general at high angle to the substrate, and this is because they commonly form the burrows in soft, water-saturated substrate. And these are examples of some fish nests, like tilapia nest here, and lungfish, as mentioned, and many frogs and toads also produce similar. And there are also fossil examples of similar structures. Exceptions, of course. Armadillo foraging pits or food probes at a high angle. These are very shallow. You can see here from above. Below, you can see the cells where the food that the armadillo was looking for. And this is a cast of the foraging piece when you can see the scratch traces and the cast also of the cells below. But these indeed did not compose, it is not a burrow system, but a shallow pit where the animal cannot fit inside. Some amniote burrows have a clear vertical development, but the helical angle of incline here is always a low degree, usually below 30 degrees. This is with the famous Ichnology diamond helix, and also with modern nesting burrows of sun monitors in this place. The angle of attack is always a low angle. What part of a burrow system we can distinguish? In this case, is a diagram for mammal burrows, especially for rodent burrows, but it can be applied to others kind of roots as well. This is modified from Hickman and Carbonato Melchor. You have some mounts, in some cases plug-in entrances or around entrances, or even mounts where a chamber can be located, but they have very low potential of preservation. Then you have some horizontal or sub-horizontal segments that are called tunnels. You have ramps, low angle tunnels, shaft subvertical, enlargement like chambers, and eventually blind tunnels and spiral. In the fossil record, you commonly will not find any mound, but the elements that are commonly preserved are shafts, tunnels, ramps, chamber, spiral. This is plan view of a relatively complicated mammal burrow with that is used to illustrate some of the architectural elements. You have entrances there in orange. We have chambers here, here, here. We have ramifications. We have tunnels, blind tunnels. These elements are important because it can be used to give an estimation of the complexity of the burrow. This is accomplished by defining segments. The segments are limited by an entrance, a ramification, a blind tunnel, or a chamber. So every of the red line that you are seeing here compose a segment. And the complexity measure following Henry and Hasiotis is summing the segments, chambers, and entrances. And this will give a 22 complexity index here. We can also take another measure, which is the tortuosity. And the tortuosity is, in this case, the length of every segment, the dashed line that you can see here, the blue dashed line, over the straight line from two distant points of the same system, which is this other dashed line. So in this case, we can also apply fractal techniques to know the fractal dimension of the system. This is not complicated procedure and can be done with a free software. And there are several ecological, biological studies that use the same technique to characterize modern burrows. So a comparison can be made. Obviously, you need a good preservation of the whole or nearly whole system to apply something like this to fossil examples. Another measure that is important is how much chambers have the system. This is the ratio that we call the chamber volume over the channel volume. So we can estimate the volume of the chambers and the tunnel with simple formulas, and obtain a radio between here the chambers in brown over the tunnels of the whole system. And applying this to modern radon system, some tips, some clues arise. Very low values of these ratio relationships are related to subterranean solitary species, like Tenomys, which is called rodents, but this is special features. Intermediate values, here we have very low proportion of chambers. Here we have some more, are related to permanent burrows of solitary species, and the higher values in the experiments or in the case that were studied by Cristina are related to permanent burrow of communal species. Here are some examples. The very low proportion of chambers. Here we have 0 chambers, no chambers at all, as composed by linear foraging tunnels of subterranean and solitary species, like Tenomys. These species feed underground, essentially. Intermediate cases, in brown, are highlighted the chambers. About 4% of the whole system, fossorial solitary species. The first case is subterranean solitary, fossorial solitary. The difference is if the animal may burrow but feed above ground or below ground. Subterranean means below ground. And finally, the highest volume of chambers are related to fossorial and communal species. They need larger chambers to allow for the group of individuals that commonly is between 15 and 50 individuals to live inside the burrow. These concepts of this idea are not new. We try to give a number or an index, but they were applied also to some similar rationale was applied to fossil studies. For example, from Xavi Ignus here, a field view and an interpretation of the burrow. From the Oligocene of Mexico, that was described by Ricardo N et al. In 2020. You can see here, the key is here, that we have very large chambers and a complex burrow system. The preservation of these cases does not allow for a complex burrow system to be described, but the authors thinks that they will represent gregarious behavior. Another example described for us is Manera Ignus. Manera Ignus is digital elevation model of the part of the septum. This is the main chamber. These are sub-horizontal tunnel. This is a ramp descending in this sense, and this is another ramp descending to the left to a smaller chamber here, which is not clearly seen. And we estimate that the proportion of chamber in the whole system is about 45%. And this lends us support to propose that this is probably a communal species. I mean, one that live in groups. It is important when you go to the field to try and obtain all the information you can. If you have three-dimensional exposure like this, for example, it is not difficult to obtain two essential measures that are horizontal diameter and vertical diameter. Horizontal diameter and vertical diameter, always regarding the tunnel axis. If the exposure is not so good or more or less bidimensional, it's more complicated. But with some relief in the exposure, you can also infer the direction of the lateral walls and the roof and give or obtain the same information. In some cases, it's not possible. It's not possible. In others, it's more easy. But if you have a longitudinal exposure here, what I marking is the burrow field. It's very difficult to distinguish in this photograph for the first time, sorry. But this is probably only useful, not probably, it's only useful to obtaining the vertical diameter or one apparent vertical diameter. Hope you can follow. Anything is okay?
Yes, thank you.
Everybody is sleeping?
No.
Why minimum diameter? I mean, the minimum diameter that you can see in a field exposure is a poor measurement and should not be used to characterize tetrapod burrows. This is a block diagram when you can see a plan view here, cross section here, or of a sloping tunnel and a sub-horizontal tunnel. And the minimum diameter here will be equivalent or similar to the horizontal diameter. Here, in this example, the same. The minimum diameter will be equivalent to the horizontal diameter, but here the minimum diameter will be vertical. In consequence, minimum diameter can means horizontal, vertical, or something between them. And it is important as much as you can, except in the case when the burrow gets loose and you cannot restore to the horizontal, but if you can, to distinguish between the horizontal and vertical diameter. And why is this so? Well, because of the directionality in tetrapod body plan. I mean, the anatomy of a tetrapod is specialized for certain orientation and locomotion due to gravity and organ arrangement. This is displayed here. The horizontal diameter is commonly reported both in extant and fossil burrows. I mean, it's a good element for comparison. And the horizontal and vertical diameter are useful for body mass estimates. Regarding the last point, if you can obtain a cross-sectional area of your burrow, you can use, with certain caution, but you can use allometric equation or regressions lines that were compiled by White and Wu et al. From different groups of animals. For example, mammal, fish, amphibian, invertebrate, reptile. This is the general regression line, and is the data of the point says used for this compilation is up to about 19 kilograms. we have found that this equation or this regression line is not good for estimating the body mass of larger, or the producer of larger burrows. For example, slot burrows, ground slot burrows, because they give overestimation. But I think that it's a tool that can be improved with more data. And for smaller burrow, we find very good results or acceptable results. Of course, not the truth. It's just an indication, but it is something that we can use. We can also estimate the ratio or relationship between the vertical and horizontal diameter, which is called relative diameter index. That was proposed by Elisamburu et al. In 2011. What is this? Well, a number between 0 and 1, or slightly more than 1, that when it's lower than 1, implies that the cross-section is horizontal elliptical, I mean flattened in the vertical sense. This is a very common shape. When it is around 1, is subcircular to circular, and is typical of foraging tunnels. And when is larger than 1 is rare, but occur in some rodent burrows, and might also imply some burrow relocation, producing structures like spriting in vertebrate Ichnology. I mean, the change of position of the burrow in vertical or lateral. Some examples: a compilation of the published radio from fossil examples is shown in these histograms. There are two histograms on the left. From the Permian Cretaceous, we have a gap in the Paleocene, in the early Cenozoic. There is no data. And then from the Eocene to the Quaternary. You can see that in the Permian to the Cretaceous, we have here the radio, more flattened horizontally, less flattened, subcircular, and vertical elliptical. The average values are about 0.6 for the Permian Cretaceous, and is slightly larger from the Eocene Quaternary. Here in this time interval, we have more examples of sub-rounded or sub-circular burrows, but we also have very low values too. So assuming that a circular cross-section is common in a fossil burrow is probably wrong in most of the cases. And this change with age can be due to compaction. Of course, older geological units will have more compacted structures than younger ones. And this should be considered. But there is a component in the shape of the cross-section of the burrow that is related to the body plan of the producer. And this is highlighted by these plastic casts of extant lizards of the genus Leolaemus that have or produce ramps that are very flattened horizontally. I mean, they are horizontal elliptical with a radio that is 0.56, a very low value. But again, I think that there is a minimum a difference in the cross-section of the burrow, but we cannot forget that some compaction may be acting on them. Some, leaving aside the numbers, some typical shapes are convex roof and bilobed bottom, convex roof and flat bottom, and subcircular to circular cross-section. These, when bilobed or kidney shape, are related to permanent burrows of communal species like microcavia, extant, some lizards. As we'll see later, there are many fossil examples similar to this. The flat bottom is related to permanent of solitary species, permanent burrow system of solitary species, and the subcircular of circular, non-permanent foraging burrows of solitary and subterranean species. Examples are Ctenomys, Chlamyphorus, and the marsupial mole. These are rodents, these are Xenarthran, this is rodent. We can also use geometric morphometric techniques to compare in an objective way the cross-sections of the burrows, and even to compare with other published information or neonological information. Regarding the subcircular to circular burrows, here we can see a cross-section of one of these Holocene examples. This is late Miocene example of this Ignogenus, Nactuignus. And this is a longitudinal cross-section showing the meniscate filling of this kind of burrows. Another example of a subcircular to circular are those burrows of the marsupial mole, not addictive, which lives in Australia. And this is a trench made for evaluating the abundance of the animal, which is very difficult to see because of the subterranean mode of life. You can see here one of them, and here, yeah. The bilobed or kidney-shaped cross-section is common from the late Permian to the present, to recent time. This is the older known example from the late Permian of Australia. This is Triassic from South Africa. This is Jurassic from the Navajo Sandstone, USA. And this is early Cretaceous from Patagonia. And this is some lizard burrows from La Pampa in Argentina. Some details from the burrow cast of the Lower Jurassic Navajo Sandstone from USA, the bottom view here above. Very few scratch traces or claw traces. And cross-section, you can see the bilobed cross-section, it's very common. And the radio that we mentioned before, the radio between the vertical to the horizontal diameter. And this is a probably possible explanation of the shape or cross-section shape that is reminiscent of a kidney. Initial burrow excavation, the burrow is left open, so it can receive sediment input, and the occupant tramples the sediment. Sediment lose urine and feces, and compaction through repeated passage produce the bilobed bottom or the central raised ridge. When the burrow is abandoned, it's left open and receive a massive sediment feed, passive, not inorganic, not related to the producer. Then some probably differential cementation occur in the lower part of the burrow, and the upper part is probably lost when watered and loose from the host rock. So what they mean, probably they are related to burrows that are open and occupied by a group of individuals. It can be traduced by communal species. Returning to the horizontal diameter and the potential importance for comparisons. Here, we compare the horizontal diameter of the burrows. These are the data, the black arrows are data on the burrows, horizontal diameter. We have two populations. The most important is small one, between 30 and 70 millimeters, and we have a larger population which is more rare. This can be compared with the trackway width of Brasilicum that also occur in the Navajo sandstone or related Aztec and Nugget sandstones. And these are the information that is plotted in red arrows below, which is compiled from several works. We can see that there is a good match between this horizontal diameter of the burrow with the width of the trackway. And it can be argued that probably they were produced by the same animal or same group of animals. Coming to estimates of body mass, we can, from the burrows, we can estimate two range of body mass between 12 and 40 grams and a larger population of 300 and more. And we can also check in the local fauna which is a candidate that is fossorial, existed for that time, and is about the size of our burrows. In this case, Cynodontia, which was a scratch digger, is a good candidate for producing the burrows from the Navajo sandstone. In this case, is recorded from the Cayenta Formation of Arizona, of the same, or roughly the same age. Another aspect of the burrows that we can use to study and interpret them is surface ornamentation. Essentially digging traces, but we can distinguish some other features that we can see in the surface of a cast. We need for describe and interpret these features to access or to view the wall of the burrow or the cast of the burrow. Otherwise, this is not possible. It's not possible to interpret them from cross-section. It's very rare. We distinguish between primary surface ornamentation that are related to claw and teeth traces. Claw traces or scratch traces in this diagram of the surface of the burrow And teeth traces here, claw traces are commonly 2 to 4. In this example, we can see a plan view of the roof of a burrow cast with several scratch traces, and here the interpretation. This is sometimes the pattern is confusing, and sometimes it's difficult to find the parallelism between the individual traces to know what is the width of the set. But in this example, you can see 1, 2, 3 claw traces that are more or less parallel. The second aspect of surface ornamentation is the teeth traces. Teeth traces are usually appear and are related to incisive of rodents. In this example, we can see one from burrow termination from the Oligocene of Mexico. And this is a famous example from diamond helix from the Miocene of USA. A second aspect of surface and ornamentation are invertebrate burrows and root traces that can appear or that occur in burrows, in the surface of the burrows. In the example that we saw previously, these snob of protuberances are interpreted as invertebrate burrows, and these invertebrate and also considered invertebrate burrows. Many fossil burrows have root traces, and this is essentially because the fill of the burrow has increased porosity that contain more water than the surrounding rock or sediment, and thus the roots prefer to go through this conduit to obtain water. This is a burrow cast, modern one, of an extant rodent. You can see here where near the red arrow, the primary surface ornamentation, scratch traces or claw traces. And you can see here also, I hope, some cylindrical protuberances, all this area, which are interpreted as invertebrate burrows made from the lumen or the void of the burrow to the wall of the burrow. Obviously, a burrow in the nature is a very important refuge for many species, and many of invertebrates can use a burrow. This is well documented, and other vertebrates too. In this case, the secondary surface ornamentation is similar to the fossil one. In the fossil one, it's very difficult to know if the invertebrate burrow was digged from inside the burrow, or simply the invertebrate crossed the field of the burrow. Another aspect is to pay attention to the burrow field. We can see here nearly cross-section. Here, this is the field, this is the host. Below, this is the field of the burrow. This is the host. And we can take time and produce a detailed log of each laminate, each bed that compose the burrow field. And we can obtain logs like this. When you can distinguish the sedimentary structures, the grain size as a normal sedimentary log, and obviously it's not very thick, and this is obviously more easy to be done with large burrows than with the small ones. But we can even take samples and make cross-sections of the burrow fields, as in this case, and we can see graded laminae from siltstone to claystone. The darker colors represent claystone, and we can see that there is a repetitive filling in that sense. We can see here a thicker lamina, but it's always capped by mud. And we can also see some cracks, probably mud cracks in the field. So graded laminae and mud cracks imply for a sedimentologist that you have dilute flows carrying a very low amount of sediment that ponded inside the burrows, clay settled, and then dry and cracked. We can also use some experiments as, for example, this burrow model run by Woodruff, and Baricchio, 2011. And you can see here the sapling tube, the burrow model, the end part of the burrow, and they pull different sediment mixings and different volumes and observe what happened. This is very instructive. They also change the burrow inclination. But to simplify the result, when they obtain a massive field, they were produced or related to en masse deposition or dense current of sediment with current with high proportion of sediment, and laminated interval were related to dilute input of sediment with a very low charge of sediment. So we can obtain some arguments or some evidence to interpret also the filling of the fossil burrows. And we can propose that each individual lamina might represent several light rains. In this case, there is no evidence of aeolian flux or dust transported by the wind. And the thicker, massive intervals will correspond to denser flows and might represent heavy rainfall. We can also to mention some variability in the sediment fillings in some examples, and we can return to the example of Manera ignus in plan view. This is, we said, a system that have a large chamber here, a ramp here, a tunnel here, and another ramp and secondary chambers over here. If we analyze the cross-section of a tunnel or ramp, we can see something like this, massive filling with mud class or intraclass, suggesting a mass deposit. And if we take a look here to the large chamber, this is a lateral view, we can see a lower part that is massive, interpretation. with intraclass and even gravel class, extra class in some cases. And then a laminated package over here that even produce some kind of crossbedding inside the film of the chamber. So we can document the filling process in some degree and in adequate situation, of course. So to finish the talk and to put most of the aspect that we have talking about in this talk, we can present some kind of flow chart for the study of fossil vertebrate burrows, not considering bone remains, simply because we don't address this question in this talk. But what kind of information we need to obtain from the field studies? First, overall architecture. Measurement on tunnel and ram cross-section, burrow fill, and surface ornamentation. From overall architecture, we can distinguish the architectural elements. I mentioned tunnel, ram, chambers, ramification. We can apply photogrammetric techniques, which are very inexpensive. We can estimate complexity, tortuosity to compare with modern or other fossil burrow system. We can obtain from a plan view fractal dimension. If the system is more or less complete, we can estimate the proportion of chambers in the system. Regarding tunnel ram cross-section, we need horizontal diameter and vertical diameter, and we can estimate the relative diameter index for comparison again and description. We can estimate the area and estimate the body mass of the producer, and we can analyze the shape with geometric morphometric techniques. Regarding the burrow field, we can make sedimentary logs, we can make thin section. Of course, there's many others kind of routine analysis that we can apply, but these are useful for interpretation of the burrow field processes. And regarding surface ornamentation, we can distinguish between the traces of claws or teeth that represent excavation, digging traces, and secondary features that are related to root emplacement, invertebrate emplacement. And we can infer here burrowing mechanism, reoccupation, root invertebrate colonization. We can trace the taphonomy or the ignotaphonomy of the burrow system using the shape, using the burrow field processes and surface ornamentation. We can also make some neognologic observation in similar systems if possible, and obtain a lot of information that is very useful to study fossil examples. And we should consider the fossorial fauna of the host unit for the age or the region, of course, bone fossils to compare with the burrow. Joining all these elements, fossorial fauna, neognology, and the information from overall architecture, relationship, cross-sectional taphonomy, we can give some idea of the paleoecological features of the producer. It's very difficult to assign to a very specific taxa or taxon. But we can say this was fossorial, solitary, was communal, left the burrows open and closed the entrances, was a single occupant or several occupants, etc. And of course, we can guess if the producer is recorded in the fossil record of the area, we can guess about the possible producer. And that's all. Thank you for the invitation. I would like to thank the IIA for this opportunity to give the talk. And of course, I was always supported by CONICET and the Agencia Nacional de Promoción Científica y Técnica in my research, and also provided monetary and logistic support from the Universidad Nacional de la Pampa. I would also like to thank my students, Manuel, Nahuel, y Silverio, here pictures, for his for inspiration about future work. Thank you.
Thank you, Ricardo. Thank you very much for this exciting and very instructive talk. I am sure that those who are here enjoyed your lecture as much as I do. And we have time for questions. So I would ask to those who want to ask a question to Ricardo or exchange some impressions to raise the hands, please. No questions?
Well, some comments. I was busy writing. Ricardo, the South Africans have described these kidney-shaped or reniform burrows, especially William Krumek, working, I think, with Amasia Bordi.
Yes.
Ah, okay. So you're aware of that. That's good. And we saw them in the field, and I did not understand the nature of the compaction and feces affecting the lower surface of the burrow and cementation. This is all very interesting.
Don't understand?
No, I
understand?
did not.
You understand?
In South
okay.
Africa, it's
just an hypothesis. No, not. You have to. We should check if this is that way. But
well, I think you have a good answer for that. And thank you again.
Thank you for your comments, and thank you. I think I just look at the clock and I spend 1 hour is too much for you. So thank you for your patience. I practiced something and I was short in my practice, but the time flies.
So Ricardo, we have a comment in the chat. Diana said, I found it very useful. Thanks for the presentation. And I don't know if we have other questions. If not, I have a question. I was wondering about the what you said that for example the elliptical cross section, it's quite difficult to be preserved. Mostly you have this elliptical. Sorry, I said elliptical. The circular cross section. It's not very putative of vertebrate burrows, but most elliptical sections. It has to do with only with the body plan, or it's most related with compaction, Ricardo?
No, I think compaction play a role in some cases, in the older ones, but I think it's more an paleoecological preferences, the mode of life. The modern exemplars are those that construct foraging tunnels. They build the burrows and looking for food, and usually these burrows are not permanent, but just used to approach to the places where they find food. This is the case with cenomies. They build a long amount of new burrows, almost, I'm not sure if daily, but frequently new parts of the burrow system are added, and the animal is moving in an area, producing new new tunnels. And I think it's paleoecology or ecology or paleoecological preferences, the mode of life of the producer that is related to the subcircular cross-section. And it's very it's related to rodents and some armadillos, pink fairy armadillos. I don't know if that is a response for your question, Renata.
No, it's fine, because I always think that the compaction play a role, especially because when you have this horizontal compaction, as most of these tunnels, they are not completely filled by the sediment input. So I always think that, okay, it's an effect of compaction. But what you said is interesting, because I never thought about that it could be related to the behavior itself for the ecological.
I think behavior is important, and of course, when you come older and older, compaction is something that you should consider in your interpretation. But the examples of very flattened extant burrows and subcircular extant burrows, especially the flattened ones, give the idea that it's not only compaction. And if the animal left the burrow open, the transit, the input of burrow, the input of sediments, the insect or invertebrate that constructed galleries inside the burrow change the cross sections. And this for sure also occurred in the past. What happened is that much more difficult to detect in fossil examples than in modern one. But I think we should pay attention to these features.
Thank you very much.
Thank you.
Any other question?
One more observation.
Go ahead.
Hmm?
Go ahead.
Thank you. The neo-ichnology of modern vertebrate burrows, there are very few ichnologists who work on this, but there's a huge body of literature on this topic, but unfortunately not from our point of view. The older works tend to map the rodent burrow systems, for instance, but the map does not include surface ornamentation or fill. And I know Daniel.
They have no field probably.
Yeah, well, but they just map them.
Yes, I know
and
this.
Daniel Hembry and his students have done such good work on this, on scorpions and such things, from our point of view. But there's so much that could be done. There are whole continents of animals that could be done.
Yes, of course. Another question that I did not treat here is how you can distinguish vertebrate from invertebrate, especially in the smaller size. We have very large vertebrate that can construct a burrow and very small vertebrates. So there is an overlap, and we are working on that to see if we can, from the literature, to propose some useful ideas. But this is what's not included in the talk.
Thank you.
Thank you.
Okay, any other question? The last one? No more questions. So thank you very much, Ricardo, for accept this invitation to bring this this excellent talk and very instructive and inspirational. I promise you that I will look to the vertebrate burrows with much more detail in the future after listen this talk, and I hope that the ones that are in the audience with us can apply all the knowledge that you shared with us. Thank you very much.
Okay, thank you to all of you, and goodbye.
Bye-bye, and we hope to see all of you in the next talk that will be on the last Friday of July. Pay attention to the social media and to the emails sent by International Ichnological Association when we let you know about the next talk.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.